Good afternoon. I'm Nivashini. I head embedded technology in UST Global. Thanks for everyone and thanks to Economic Times. Before we get to the topic, I would like to give a brief about UST. So I'm part of UST past 7.5 years with 20 years in industry. I'm pleased to be part of this event representing UST. We started our journey 1999, 21 years back, currently with the strength of 26,000 employees with presence in 25 countries, having 140 plus client base. So our PES is 5,000 plus with 8 major clients based in semicon, 6 offshore and nearshore, supporting 360-degree engineering right from pre-silicon to automotive across the globe. So my motivation is to discuss how automotive embedded OS is influencing the software innovation as we are much fascinated and abreasted about connected vehicle ADAS and autonomous journey. So I will take you through the automotive software development trends and quick comparison of all OS and our platform. So to start with, the definition of the future automobile is going to be ST, is electrified, autonomous, shared, connected, and early updates. So you would have heard about these 5 words number of times in different contexts. All 5 are interlinked, be it autonomous, which is closely linked with connectivity and only has a business case when it's shared. Autonomous driving needs to be independent when we are going to have electrical technology. So before we go into much detail, I would like to define the XC. The first aspect, electrified. The transition to emission-free hardly be possible without electrification of the drivetrain. So emission-free is a global initiative. In fact, if you see the predictions, over 55% of all new car will be fully electrified by 2030. Second aspect is autonomous, where we don't have to drive is appealing. We are working towards determining how to provide safe, economical, and driverless software and hardware features. So thanks to all rapid progress in areas of AI, ML, and deep neural networks are embedded. Third aspect is shared on-demand service on user convenience. So because of this trend, this vehicle inventory has fallen significantly in some markets in light of increased utilization of the field. Fewer vehicles will be required in the future. Fourth dimension is connected, is networking of cars with the outside world. It's representing two concepts. One is vehicle-to-vehicle communication. On the other hand, it is occupants networking with outside world. Last aspect is models getting early updates. Earlier model life cycles were 5 to 8 years, but nowadays the range of models shall be updated annually in order to integrate the latest hardware and software development. The short innovation cycles entering the market primarily through regular updates. So vehicles that are used in the traditional way will remain in the inventory for comparatively long time. But in contrast, autonomous, in particular, shared autonomous will be changed far more frequently, resulting in rising sales. What it means for the software development or software companies, we need to expand R&D in software solution instead of product range, which is already showing a stronger growth. Next, I would like to touch upon the automotive software development and its trends. This is majorly derived by 5 dimensions of whiskey I just talked about because it's dramatically increasing the amount of processing and data flow. So IVA systems as such becoming more complex and feature rich. Example, driver information system such as clusters and heads-up display. In fact, a mirror replacing the cameras. So all require displays that significantly change the design of the cockpit. Finally, electrification is also burdening the software in terms of additional monitoring capabilities to monitor the energy and the battery storage. So these are the 9 key attributes. So prime most is the ECU functionality consolidation. So there is an increase in software functionality requirements. So we have to change the vehicle system architecture along with feature-rich silicon platform. For that matter, virtual ECUs are becoming more common with embedded virtualization and hypervisors. The second aspect is the ASIL, it's basically FUSA, which comes under the IS 42662 standard. So this is ultimately influencing the design of a platform. We are addressing early in the design process. Third aspect is the connectivity. So where we need to talk about the vehicle architecture to support more than one vehicle to cloud network. So what it means is we need to take care of the security, which is the fourth aspect. So two-way security is the focus of importance to prevent vulnerability that can cause vehicle as well as within the vehicle. The fifth aspect is the over-the-air updates. So gone are the days when vehicles gets into service center, and nowadays ECUs are updatable OTA, similar like mobile phones, the smartphones of these years. Sixth aspect is leveraging open source software. So more OEMs and tier ones are adopting open source. Majority ones are Android and AGL, where AGL is supporting 15 Linux distros. The obvious advantage of OS, it supports safety use case with the initial low cost of entry. ECU with safety requirements is composed with certifiable hardware and software to support safety use case. Simply to put, investing in previously certified software elements is risk reduction. The seventh is this sensor fusion, example of autonomous. So active safety and self-driving systems are increasing the usage of sensors, and single sensor-based learning is not descriptive enough. The challenges are various factors. So sensor fusion is the combination of these. In fact, it is culmination of various sensor information smartly bundling and give autonomous vehicle a 360-degree view of the environment. So we sense, we perceive, we localize, and then react, as you can see in the right side of the picture. Eighth aspect is knowing where to use proprietary software and certified software elements. Examples are the safety certifications coming from either SLD or SLB. So we as a software partners, we have to make sure all the elements which gets into vehicle are certified, especially like ATAs and hypervisors. The ninth aspect is long-term support requirements. This is the car buyers expect cars to continue to be fully functional, which means OEMs will have long-term support requirements. So all these nine factors creating a major challenges in the software architecture. So we need to increase the compute platform to make sure the connectivity and sensors, the safety and security aspects, and the vehicle system architecture to accommodate the performance. We need to look for a holistic approach so that we reduce the latencies of multi-ECU communications. We are also looking at having some elements being centralized and some elements being distributed in architecture. And the other way, the simulation at vehicle level is also playing a huge role in reducing the risk in the integration process. The third aspect is security and safety at a system level. Like I mentioned earlier, FUSA and security is imbibed as an engineering practice and implemented at all levels. So this is applicable for hardware and the software perspective. Ultimately, we as an embedded solution provider, we keep these factors addressing any reduction in risk, schedule, and options of having other hardware suppliers also. So when I talk about risk, we ensure we have previously certified software element, which brings in huge confidence for safety certification at the system level. From schedule perspective, we bring in experience, solutions, and services, so that that also gives in development reduction in terms of cost and go to market. Examples are making use of hypervisors and the microkernel kind of architecture. Third is, like I mentioned, is having more than one hardware platform supplier. So as an embedded service provider, we have support in almost all the hardware, which is specific for automotive development. So next, I would like to talk about auto operating system. Just to briefly classify what are the types, and I would like to compare the operating systems with open sources. So basically, it is classified into five types. The basic auto, wherein the QNX and Linux are the ones, including system kernel and virtual machines. The second one is the custom made. It is deeply developed, tailored, and based off the basic OS. In fact, the Volkswagen and Baidu uses the custom made auto. Third is the ROM based auto. It is again customized based on Android. It's being widely adopted by Benz and VW. Fourth is Super Auto. It's basically an app home mapping system, similar, for example, of Car Life and CarPlay. Fifth one is the neutral and free OS. That's where the AGL and Android ecosystem comes into place. Android ecosystem comparatively is more mature but widely used in Chinese OEMs. We knew that OEMs felt risky to apply Android as Google banned Huawei from using Google mobile services in 2019. So hence AGL become a vital choice. Now AGL has support of 11 OEMs including Toyota, Volkswagen, Nissan, Subaru. What it differentiates is AGL addresses 70% of OS development work, while the remaining 30% can be developed by OEMs. So more than 140 AGL members work together to develop a common platform for infotainment, and we are also part of it, which will be further available for ADAS, OTA, gateway, V2X, and automated driving in the future. So next to highlight the differences and similarities between in terms of architectural for the AGL, Linux and Genevi. So AGL, Linux and Genevi are based out of monolithic, whereas QNX is microkernel based. When I say microkernel, even the device driver sits on the top layer. So it means that kernel implements only four basic services like scheduling, communication, and networking, and interrupt handling. However, both Linux and QNX are POSIX compliant. That means API and utilities are same. And in fact, Genevi OS and AGL were launched together with different goals. Genevi wanted to promote Linux and open source in the automotive market, and it did a fantastic job at that. But the focus with Genevieve is on the spec. Some components were still licensed and the compliance program. It was never about actual distribution or a common platform. It's more about developer building their own platform and making it compliant. That's a note for AGL. It was started as a distribution reference platform from there. So next, I would like to talk about why AGL platform is the obvious choice for the automotive industry, since it is the only group addressing all the software in the car, that is from the infotainment, heads-up display, cluster, ADAS, and it's truly leveraging the synergistic software at scale. So UST is instrumental in platform built on NXP IMX8 at its core, wherein automotive grade Linux is runs upon Yocto, which is serving as a single platform for entire auto industries. So thanks for all fish. We are using icefish to jellyfish version for our infotainment platform. As I said earlier, Agile has changed the automotive approach because of its open source. It also addressed the real-time capabilities of QNX by means of real-time patch, example, or preemptive scheduling, where we could achieve 99.9% of determinism versus 100% in QNX. Underlying technology is not that different. It still uses the kernel, middleware, and source components, keeping the reusability during the development. However, we have had to more focus on the fast boot and security since it's infotainment and ADAS. So we need to also access the vehicle canvas. So our platform is the first time to run AGL on IMX site, addressing on innovative vehicle software architecture, which I just talked about on the disruptions on the automotive software, which would help us in scale and reduce the GTM, is also driving the central console with multimedia, radio functions, HVAC functions, navigation, and also ADAS features like rear view camera and parking assistance. So we have used software isolation as a security measure against possible vulnerabilities brought by application installed after the market. So apart from these solutions, we have enabled UI UX strategy with Qt and HTML5. This can be fine-tuned on OEM requirement. So we can enable seamless porting of AGL and development on any other SoC that includes Intel or NSS or TI chipsets. We have holistic approach for telematics and connectivity in collection of telemetry data from vehicle. Also, the cloud connectivity gateway also support installation of edge services. So like I mentioned earlier, as a step to ADAS, so we use GPU as a combination of OpenCV and OpenCL and with sensor feature extraction. So this is giving a multidimensional sensor for recognition, leveraging NXP's edge intelligence. Having said, we focus on security enhancement to protect the OS from any possible intrusions. So we support multi-OS features using hypervisors. So that's a greater advantage. We could have multi-domain in a single SOC, which means that we bring in a cockpit platform. While Agile is an obvious choice for automotive IVI, you can help making the process smoother. We can work with you to identify unique features that will help differentiate your platform from the competition. Next, I would like to touch upon the complexity of embedded processing, which we are taking care while we moving towards the autonomous level 4 and level 5. Like you mentioned earlier, there's a lot of sensors being handled independently for ADAS and autonomous level 3. But to truly to have autonomous level and 4, there is a prerequisite to use sensor fusion, basically culmination of radar, camera, and lidar to build autonomous. So each sensor modality has its own strengths and weakness. For example, if you say the camera, we get good texture and color, but cameras are susceptible to conditions like fog and rain. But radar and lidar are both active and more accurate than cameras at measuring distance. So far, machine learning and autonomous is used individually on the output from each of the sensors. However, for autonomous, by combining all the outputs from different sensors, we get a more complete picture. In fact, we give a 3D image with the point clouds, creating a better clustering and more accurate by applying machine learning using TensorFlow. So added advantages in case there is a failure of a camera, the lidar and radar would deliver the same field of view, bringing a certain level of redundancy. So this completes the sensor and the perception, which is primarily taken care in the sensor perception domain controller, which means we process the elements of intersection of field of view, and we also take care of the object fusion. For example, any object generated from the camera, we find its corresponding object from the radar and vice versa. All happens in the perception domain controller. Then we fuse the software data into automotive Ethernet to system domain controller, where we form localization and fusing the map. Along with this sensor fusion, so when we localize, the vehicle come to know the situational information and also have the self-awareness. So we also help in doing behavior prediction and planning. So to build a road model and predict actions, also trajectories of other dynamics. So running all these workloads concurrently is requiring high processing power in terms of software implementations and advanced neural engines. This has increased the throughput data pipes as well. This is the overall ADAS complexity which we are handling and the platform is all about. So next I would just touch upon the ADAS feature which we have in terms of software implementation. This is lane departure warning, parking assistance with roadside recognition. This uses the fusion of various sensors to bring in the insightful information to the driver, to the vehicle, and also to understand where the vehicle is all about. So with this, I would like to play a short video.
You have arrived at your destination.
Thank you. This is the short demo of the platform that includes the infotainment and ADAS. So we can rest assured the platform meets all the demands overall from UST embedded services and ensure real products behave as designed and closed loop with continuous improvement. You could really plan your integration and manufacturing, keeping these points into consideration. That's all from my side. We can do a lot together. Thank you once again. Thank you.